are you all able to see the screen?
Yes, ma'am. It's visible.
So, can I start or should I wait for some more time?
We can start, ma'am. We can start.
Okay. Warm good afternoon to one and all. So, myself, Dr. Asha, faculty from Department of Civil Engineering, CMR Institute of Technology. So today I will be addressing on the geotechnical aspects in a lake restoration. So I have outlined my contents into this fashion: introduction, a bund and its parts, then selection of earth for a bund, then properties of earth, then construction process, and what are the general distresses that we encounter in an embankment, and how do we detect it, and what are the measurements that we can make in order to have a prior knowledge about the failure in a dam or an embankment or a bund, and what can be the probable remedial measures. And then I would just like to summarize my session. So before I start my session, I would just like to extend my sincere acknowledgements to my institute for giving me an opportunity to be a part of this session, and Friends of Lakes as well as ATRI for inviting me as a part of this session. And I have used many web-based resources for clarity.
Dr. Asha, sorry to interrupt. Your volume is quite low.
I can increase the volume. Yeah.
Sure, sure.
Am I audible now?
Yes. Maybe the mic can be a bit closer.
Is it echoing?
No, it's quite soft.
There is no audio at all.
It's quite soft, actually. Yes.
Should I do anything with respect to the audio?
We cannot hear you, Dr. Asha.
Oh, is it? Okay. But I have kept my audio to the maximum. And is it the same with everyone? I don't know.
No, you will have to relog
I can
in.
hear you.
And
I can hear you,
please
madam,
check
very
your
well,
audio.
clearly.
No, it's quite clear. It's quite clear.
Yeah, it is very clear.
Should I do something?
Yeah, I can hear very clearly. No problem.
Okay. Shall I continue?
Ma'am, please continue.
Yeah. So as I told you, I would just like to extend my acknowledgement to my institution for giving me this opportunity, Friends of Lakes and ATRI for having me a part of this session. And I have used a couple of web-based resources to explain the concepts and things. So sincere acknowledgement to that. And I have taken the specifications or with respect to any other particulars with respect to the Indian standard codes or with respect to Indian Road Conquerors code books. So sincere acknowledgement is due to all this. Now, start the session by to start with this water bodies in general. So we know that we have a good amount of water bodies in our earth, and we have oceans, we have sea, we have river, we have lakes, and we have ponds. Out of this, we can say that the ocean and sea, the water that is available from that is more or less salty, and because of that, it is not being used in our domestic purposes as well as in the conventional uses and things like that. And river body also, it is being used, but at the same time, there are chances that the river bodies will also have some amount of saline content in it. And I can say that the river also may or may not be used for domestic purposes. In this context, lakes and ponds form to be a very important resource for water. And both these terms sound quite close. So that is the reason I have just put the differences as for lake and ponds with respect to the depth. Pond is a body which is very shallow, and whereas a lake is something which is deep. And now, what is the importance? So in my session, I'll be speaking throughout in terms of lake. So how exactly lake is important as a part of a life itself? So we know that lake is a system which constitute an ecosystem by itself. We have plant life as well as animal life being sustained within that, and thus lake forms an important part in our life cycle itself. So this is a general picture because we know that Bangalore is a place wherein we have a good number of lakes as well. And however, the lakes are more or less, I can say to some extent, polluted as well. Now, I would like to take you all from this lake, okay, which is a macro part, to a small part of a lake, which is nothing but BUND. Okay, so BUND is nothing but what you can see here in this, you can see here jelly is being placed over here and it retains the water body. So I have taken different views of that, and here you can even see the case wherein the bunds are being sophisticated with respect to railings so that it can be used by a person for recreational purposes as well. Now coming to BUND as well as its cross section. Now what do you mean by a BUND? So BUND is a structure which is constructed and it protects a water body and it is made up of earth. Okay, so water body, when I'm telling, it can be a lake, it can be a pond, or it can be like upstream side of a dam or anything of that sort. And it will be running around the entire perimeter of the lake. And we all know that a BUND is made up of earth material. Okay, basically it is meant to retain the water, and it can even be constructed using brick or concrete blocks. And at the same time, sometimes they are even being used in order to retain the chemicals from leaking outside the walls. Generally, a cohesive soil. So I will be speaking more about this cohesive soil and things in the later sessions. So cohesive soil is used to prepare the BUND as it has a very low permeability and retains water without leakage. Small layer of gravel is also placed around it to guard it from erosion. I will be highlighting more about this throughout my session. Now let us have a very close look onto a BUND and its cross section. So this is a typical cross section of a BUND. Here you can see that the slope here, let me start with all the elements that are present in this cross section. So this is your top BUND level, and this is going to be your mean water level. You are having, you even have something called as NWL, which is called as a normal water level, which is not marked here. The difference between the normal water level, so normal water level will be something like here, it will be coming somewhere here. So the normal water level and the mean water level, the difference being the freeboard. So the objective of this freeboard is to keep a clearance so that the dam remains protected. Now, we have something called as a revetment that is provided on the top. We have a lining that is being provided. Okay. And here you can see that the center part, we call this as a core of a dam. Okay. So this part is called as a core, and the outer, this orange part, we call this as a casing, or we call it as a shell. So the hearting is also called as a core, and the casing is also called as a shore. We generally have something called as a cutoff trench. So this cutoff trench, the objective of this cutoff trench is basically to ensure that there will be a difference in the The water will not come from the upstream to the downstream end. So this will be something like a cut-off wall, and this cut-off trench generally will be extending from the base of the dam to an impervious layer below. So I repeat, the cut-off trench, or I can say that this is going to be the foundation part. This will be extending from the base of the dam, or I can say that the earthen dam, to the impervious layer below. So this part is also comprising of a material which is having a very low permeability. I will be speaking about these technical terms in detail in the upcoming session. And also you can see here some designations here. I'm not sure how much everyone knows about these classification as such, but I can say like this is SC represents a sandy clay. This is called as sandy silt. S is for sand, C is for clay, and M is for silt. This is a clay of low compressibility. This is silt of low compressibility, clay of high compressibility, again silt of high compressibility, or any other soils. You can see here, this is part is comprising about gravel, gravel well graded, gravel poorly graded, sand well graded, sand poorly graded, then G of C, that is gravelly, clayey gravels, and then clayey sand or any other soil of that sort. Now, you can see that this core, it will be extending from the base of the depth, I mean the ground level, to a height. Okay, it is not necessary that it has to extend like this. Sometimes even it can extend to the top, but generally it will be having a gap between the free surface and the towards the top of the core. And you can even see that this part, this part is nothing but called as a sand blanket. I will be telling about these terms in detail in the upcoming slides, because the reason why we provide the sand blanket is by any chance, any chance the water appears to enter the bund, it should find a way to come out without disturbing the structure. And that is the purpose of having the sand blanket in the toe end. So this is nothing but called as a toe, and this is a heel. And another thing that we have to keep in mind is the core is generally the one that forms the heart of the dam or embankment or a bund. That is the reason why it is called as a hearting, because the entire structure of bund is constructed over this hearting. So the entire bund will be constructed over this hearting. It will be staying there, and it is a material which will be having a very low permeability, and the casing is a part which will be having a very higher permeability, so that any water that enters, water can enter this part, but however, to prevent this coring action and all only, we will be having a gravel cover over here. And I'll be speaking more about this, as I told you, in the upcoming slides as well. Now we can even have for the toe drain protection also, like we can have a drain wherein the water that is collected can be discharged away. And we are even having the specifications for upstream slope as well as a downstream slope. Now, what do you mean by 2:1? So 2:1 refers to the case wherein it is 2 horizontal to 1 vertical. So you can see from this figure itself, 2:1. So that means 1 vertical and 2 horizontal, which is nothing but corresponding to a slope of 30 degrees. So here generally we will have a bund which will be of a slope which will be lesser than 45 degrees, because too steep a bund will always be subjected to erosions. But it is not the case wherein we have to provide the sufficient protections and things. Now coming to the selection of earth for a bund, what are the different types of soils we can use? Soil, definitely a soil, a muram soil, or we can have a gravel, or we can have a reclaimed material from pavement, fly ash, pond ash, or a mixture of these. The reason why I'm telling a mixture of these is because these days we come across a lot of cases wherein stabilized soil is being used for this BUND construction. And generally, people will have a feeling of what about this expansive soil? I'm not sure how many of you know about this concept of expansive soils. Expansive soils are soils that have a mineral called as montmorillonite mineral. So because of this mineral, what happens is in the presence of water, this soil will try to start swelling, and thereby what happens is like it will uh, increase its volume. And generally those soils we don't prefer for construction. However, not for the top 50, not for the top layers 150 mm. Below that we can even use an expansive soil for a fill. So the expansive soils generally with the freeze well index less than 50. Now, example for a typical black expansive soil is like black cotton soil or a bentonite slurry and things. And the advantage of this expansive soils is like once it has swelled everything, definitely it will be having a very low permeability. But at the same time, they generally belong to the group called as clay of high compressibility. I will be telling you about those things later. Now, don'ts. You should not use a material directly from swamp or marshes. Okay, why it is so? That also I'll be telling you. But however, you all know that whenever we walk on a marshy area, we always feel that our leg will be going inside, right? This is because of the poor shear strength of the soil. So such soils will always have a very high amount of compressibility. So such soils are not a suitable material for these embankments. Similarly, peat, logs of any soil that contains logs, stumps, and perishable material. So these, and again, soils to be classified as OL, OIOH. OL means organic soils of low compressibility, intermediate compressibility, and high compressibility. PT is nothing but the same. I've already used PT. Peat is nothing but the PT. Then materials which are susceptible to spontaneous combustion, a material which is in frozen condition, a clay with a liquid limit greater than 50 or plasticity index less than 25. Greater than 25. I know that these terms sounds to be quite technical. I will be coming to that in the subsequent slide so that you all will be having a feel of what it is. And materials with salts resulting in leaching. So these are some of the soils that we don't prefer to use for the construction of a BUND. Now, as I told you, you could have seen when I showed the BUND itself, you could see CL, CH, SC, GC, so many things. So we can say that whenever we want to select earth for a BUND, soil classification plays a very, very important role. And then comes the compaction characteristics. Then comes permeability. And definitely the shear strength is also an important parameter, but generally that will be coming into consideration with the classification and permeability characteristics itself. Now, how do you classify a soil? You get different types of soil in the field. How do you classify it? In order to classify a soil, we generally use particle size analysis. Generally, people who work in the field, they may sound weird, what exactly do you mean by this particle size analysis? It is a very, very important part, especially to know which type of soil are we dealing with. And similarly, the plasticity and grading characteristics of the soil. So I will also give you some tips on how to particle size analysis. We have something called as sieve analysis as well as sedimentation analysis. So whenever I'm telling sieve analysis, so we generally use something called as wet sieving. Okay. Now, what do you mean by wet sieving? Now, to help you understand what is the need for wet sieving, I will tell you a simple example. Assume that we have a heap of soil that is there on the field. It happened to rain yesterday. Yesterday it rained so heavily and your heap of soil also has got wet. Now leave it there. You couldn't do your work for the next day. Leave it there for the next 2-3 days outside wherein it has been exposed to sun. You can see that the moment you take the soil, you can see that this soil would have formed some lumps. These lumps, if at all you just like that, try to do a sieving, or because the lumps will appear to be so strong that you may think like it is a coarser grain material. You may feel that it is a bigger size particle. Definitely not. So in that case, if you put some water to it, you can see that the lump will break. The lump will break and it will get powdered. So because of that, we always want wet sieving to be carried out for this soil. So the reason for the wet sieving is because the lumps will break and you will get this all the lumps being fine powdered, and you will be able to identify the correct size of the particle. And always the 75 micron size is very, very important as far as soil classification is concerned. So I'm just trying to link you. The reason why I'm telling all this is because, as I told you, in a typical BUND cross section, we have GC, SC, and all those classification. Similarly, we have CL, CI, CH, and all those things also. So what is that? So to understand that only, I'm going through all these things. Now, generally, whenever you deal with the soil, you have particles that are having a size in the range of 80 to 300 mm, classified as cobbles. So we call those particles as cobbles. Gravel is something which is having a size between 4.75 to 80 mm. But generally, people in field, they don't have a segregation like cobbles, gravel, sand, like that. They will be mostly sand they may use, but otherwise they will use the term jelly. So we have gravels of particles or size in the range 4.75 to 80 mm. Sand is something which is having a size between 0.075 mm to 4.75 mm. Silt is something which is having a size between 2 micron and 0.075 mm. And clay is a particle having a size less than 2 micron. Now, what do you mean? You have seen there, right? GC, SC and all. So, cobble, gravel and sand, together we call them as a coarse grain soil. Similarly, silt and clay together, we call them as fine grain soil. So silt, as I told you, we have the denotation as M in your grain size analysis. Cobbles, we generally don't specify as such. Then we have gravels. Then we have, so that also we have seen in the embankment cross section, G. S is for sand. Silt is nothing but M, and clay is nothing but our C. So I can say that can I continue? Yeah.
Yes, please. Please continue.
Yeah. So I can say that 75 micron is my critical size that demarcates a coarse grain from a fine grain. Might be you all will be wondering, what is a 75 micron? Is it so important? Construction of a BUND. Now, just to give you a feel of how exactly this wet sieve analysis and all is, we have a grain size analysis. So this is how the wet sieve analysis we do. And I'm not going to the details of the experimental part because generally we add some amount of uh, reagents in order to break the lumps and all. I'm not going to those things, just to make you have a feel of how this is how we collect the soil and we make it into a slurry form and filter it. And now you might be wondering, where is the 75 micron and all coming? Yes, we do have a set of seals that segregates the particles into different size. Based on these, we make a graph. Based on these, we make a graph which is called as a grain size distribution curve, wherein we make particle size. We don't use the word C size because we have already used the C to categorize our material. So we have particle size and we have percentage of materials. We have different types of materials over there. And this is the way in which we classify the soil. So this grain size distribution curve plays a very, very crucial role in classifying the soil. Now, before going to the classification consistency part, now I will tell you, now I have told you about coarse grain, fine grain. Now, how do you identify whether it is sand, whether it is going to be silt and things? So this all depends upon the this graph result. I'll be telling you about that in the subsequent slide. Now, coming to consistency of soil, which is a parameter for clay, because you have seen there, you have seen the word. So you have seen something called as the clayey soils. We have this term called as consistency because I have used in one of the slide as plasticity index. So the plasticity index is decided in terms of consistency. So generally a clayey soil, if you take, okay, you can take the soil, suppose it is in an oven dried form. Okay, it is dried, completely dried form, because generally how much ever dry you feel the soil is from the field, you can see that it will have at least 3 to 4% of moisture in it. Okay, I'll be telling you how to determine those things and all in the later sessions. So we have a dry soil. So this is the way in which we have. Suppose you add some water to it. You can see that this initially it will remain like that. Still all the voids are filled with water. Afterwards, you can see that it will change its consistency. So you all know that our Ganesha, during our festival of Ganesha festival, excuse me. Yeah, so during our festival time, the Ganeshas that we make is also made up of soil. So which state our soil should be to make it in the form of a Ganesha? In what state we can make the soil into a Ganesha part? Sometimes you can see that initially whenever you tried making something in the some water content, you cannot do that. Generally, whenever you want to make any molding part, your soil should be in plastic state. So this consistency plays a very, very important part. And similarly, you can see that generally sometimes any failure happens, the soil will start moving. You can see flowing. So this is a condition wherein it will have a negligible or low shear strength. And we call that the soil is said to be in a liquid state. Okay. So coming to the classification of soil. This is a very, very important part because now I told you about G, C, SC, everything, and similarly CL, CH, and all those parts. So you should know when can you put those names, where exactly you can put it. So whenever, suppose you have, before, rather than telling this part, I will just tell with respect to some numbers and figures. Assume that I have taken 300 grams of soil for my experimental studies. So whenever I'm telling all these things, because we deal in kilometers of stretches, you may have to do it for a couple of intervals, okay, wherein you can identify the sampling based upon the texture of the soil or based upon its color and things like that. And anytime, whenever you take, you will be getting, say, whatever the quantity you get, you have to sample it well so that it will be a representative sample. And suppose in that, from the representative part, you have taken, say, 300 grams of soil. Now, this 300 grams of soil, I have put it onto a 75 micron seed. Keep in mind, I am doing a wet seeding. So 300 grams of soil, I have put it on a 75 micron sieve. And I can see that suppose after doing wet sieving, the material that is retained on the 75 micron sieve, because finer than that will pass through it. So suppose around 160 gram of soil is retained on my 75 micron sieve. I repeat, 300 grams of soil I've taken. After doing wet sieving, around 160 gram of soil is there on top of my sieve, that is 75 micron sieve. If that is the case, I call it as a coarse grain soil. So 300 grams of soil, suppose 160 grams is retained on it, we call it as a coarse grain. Suppose it is only 140 grams that is retained, or assume that it is only 149 grams is retained. What does it mean? 151 grams has passed through the sieve. We call it as a fine grain soil. So this demarcation is very, very important. So generally, you can identify this classification properly only by doing the classification in terms of wet sieving. Now, assume that my soil is coarse grain. So I repeat, suppose 300 grams I've taken, 160 grams is retained. It is a coarse grain soil. Now, I can say that I have two parameters. I can say not two, I can say 4 parameters are there. If we have some terms called as uniformity coefficient and coefficient of curvature. I'm not going to tell you all these things in detail. I can just tell you this. Uniformity coefficient is a parameter that decides how uniform the particle sizes are. And I'll tell you, you can get these parameters from your grain size curve. So how it is linked to here. So grain size curve, you can get all these details, and knowing the fines. So when I'm telling fines is something which is less than 75 micron in size, I can put it as gravel well graded or gravel poorly graded, silty gravels and clay gravels. Please note, I'm not going to highlight on IP values and things like that, because it is, IP is nothing but liquid limit minus, just a minute, I will just show you here. Yeah. So the water content at which the soil changes into liquid limit is what we call it as liquid limit. The water content at which the soil changes into plastic limit is called as plastic limit. And the difference of these two, we call this as plasticity index. Keep in mind, we have all these things, we can determine all these things by standard procedures. We can determine the liquid limit of the soil by different methods. We can determine plastic limit by different methods. Everything we have standard procedures, but I'm not telling all those things because it is only for you to have an awareness that we have a concept of liquid limit, what plastic limit, everything that determines the consistency of your clayey soil with respect to water content. So we have, so I told you, we have gravel. This is based upon the fines, and we have the two parameters called as uniformity coefficient and coefficient of curvature. So I have told you these terms. This is because these terms you would have seen in the cross section of the embankment. So that is the reason why I have told you. So please note, so this means the importance of these tests as well whenever we are going to restore a dam bund, I mean a lake bund. Similarly, I have my fine grains. So again, I am having my sandy soil also being classified. So generally, coarse grain soil, I have it divided into 8 groups. 4 groups are for gravel, 4 groups are for sand. Okay, and I have my fine grain soils. And actually we have a peat and marshy soils. So whatever the classification I'm telling is the Indian standard classification, IS classification of soil. And this is a classification of fine grained soil. Here I will take some time because I want to help you all understand this part, because in the graph, in the embankment cross section also, because I have told there all these terms. So just I want to tell you about this. So this is clay of low compressibility, clay of intermediate compressibility, clay of high compressibility. We have a line, and this line, we call this as A line. We call this as A line, And this is a line that demarcates silty soil from a clayey soil. So this is a line which demarcates a clayey soil from a silty soil. Based on these things, and we have something called as organic soils also, which come below. And please note, this entire classification is based upon liquid limit and plasticity index. So please note the importance of these parameters as far as the soil classification is concerned. So this is what exactly I told, the gist of it. So I'm not going to tell more about this. Now, I have told about so many things in the sense, liquid limit, plastic limit, silty soil, clayey soil. But how do you do all these things when you are in field? No, it is very difficult to do all these tests in the field. And for example, in the prima facie, if you want to make a decision or so, you should always have some rules of thumb wherein you can make a decision on your own. So in that sense, I would just like to highlight a few tests which help you to distinguish between clayey soils or silty soils and things like that. Now, dry strength test. You try to have a lump, okay? You can try to have a lump and you try to crush it with your hand. Take a lump of soil, try to crush it with your hand. You can see that the strength exhibited might be, if it is too high, it is a clayey soil. A lump in the dry form, you try to crush it. If it offers a great resistance to your crushing, it is called as a clayey soil. Because if it is a sandy soil, that you know, if you take a sandy soil, you put it in your hand, it will crumble. You have something with a silty material, it will crumble. Now, what exactly do you mean by silt? Probably all of you know, you would have seen that anything, it makes a material shine. You can see that it will be mostly giving a shining texture also to your soil. Then a quick method to understand whether it is a coarse grain or I can say cohesive or non-cohesive also I can say, because I have used the word cohesive and non-cohesive. So I can use this word also, or I can say with respect to silt and clay also. What you can do is, you can take a small amount of soil in your hand, put some water to it and try to shake it. Okay. So you can see that if at all you are able to see the water that is coming up. Okay. If you are able to see, if it is not able to retain the water itself, you can see that it is going to be a sandy soil. Okay. Now, another test by which you can identify a silty soil. So this is mainly the method that we use for plastic limit test also. Take the soil from the field, try to make into 3 mm diameter rods. So when I'm telling 3 mm diameter rods, you might be wondering, how do we do this? Is it like we have to have a 3 mm diameter something? Yes, generally that is the way in which we train the students also. We can have a reference nail or a wire or something like that. You can have it, and you can, if you're able to make fine threads, then it is a clayey soil. If you are not able to make a thread and your thread crumbles, then that is a silty soil. So we can say that in this way, you can easily identify a silty soil and a clayey soil. Now, in order to have a broad classification, take some soil in a container and put some water to it. If it is a sand, you can say that it will settle in 1 minute. If it is comprising of silt, it may take 2 hours. And if it is a clay, generally the water will remain in suspension itself, and it may take days to settle. So clay layer will take days to settle, but generally it will be remaining in suspension. So the reason why it is so is because, as I told you, clay particles are always lesser than 2 micron in size. So how do we determine this particle size? Generally, you might be wondering, because 75 micron and all, we have Cs. Okay, and in fact, in the previous slide, I have shown you the Cs. Generally, we use the Cs there. But how do we separate out this clay silt percentage and all? We have something called as sedimentation analysis, which is based upon probably the engineers over here or anyone who would have studied in the physics in the lower classes, Stokes' law. So based upon the sedimentation principle, we will be able to identify the percentage of clay and silt. I'm not going to the experimental part. Now, let me go to the properties of the soil. So these are all with respect to classification and identification of a soil for the BUND. Now, let me go to the properties. This is a very, very important part as far as the construction of embankment is concerned. Now, what do you mean by compaction? Now, you take any soil from the ground, any type of soil you can take from the ground. You know that it will be containing soil grains. It will be containing some amount of moisture. As I told you, even if you feel the soil is dry in the outside, you can see that if you do a proper water content test, you can see that there will be at least say 3% of water in it. Okay, so 1 to 3% of water in that. So that will be there. And also there will be a lot of air. So it is very difficult to segregate your particles in your handful to this. But for our ease and convenience, we have segregated them into solids, water, and air. Now, you apply any sort of mechanical means. You apply compaction, you try to roll something on top of it, you try to tamp it, you try to put some weight on it, any mechanism of that kind. And thereby, if you are able to reduce the air voids in it, we call this as a compaction process. Okay, this is a very, very important part as far as the embankment construction is concerned. I'm not telling you more about these details. Basically, I just want to tell you that because these are all the laboratory part of the test. So generally, we can determine the the compaction characteristic of a soil in the laboratory. So I can, rather than telling this, I will tell you with a simple example rather than explaining this entire picture. I can tell you like you take some soil, okay, and I'm asking one person to put this inside a box. Okay, so what happens is like as such I have taken say 1 kg of soil from the field and I'm asking the person to put it inside the box. So what happens is like he will try to put his own mechanism to compact and he will try to make it. But what happens is like he will attain some volume, okay, and if I ask him how much mass he would have filled in that mold also, he will be able to tell. After that, I'll ask him, you add some amount of water to it, say 2% water, whatever the soil you have taken, you just add 2% of it, you put it. I can see that this time when he compacts it in the similar fashion, the sand or the soil that is left out, that is not going into the box, will be less. I will tell him to do this, with different water contents. You can see that as and when I increase the water content, you can see that almost all the soils goes inside. But after a period of time, everything, whenever, for example, suppose he has added some water and assuming that as and when I'm telling him to compact, you can see that most of the water will go inside. But if you try to find out the amount of soil grains that has gone inside, you can see that there will be always a trend of this fashion. There will be a trend of this fashion, which is nothing but like this, wherein this is the dry density and this is the water content. You can see that the dry density will increase and after a point of time, it will start decreasing. Initially what happens, this water you put it will lubricate your soil, it will keep on coating your soil, it will help in filling it. Afterwards, it will afterwards, when you compact it, you can see that more water only has entered into it. So because of that, what happens is like the amount of soil grains going inside will be less. So this dry density of soil, okay, is a very, very important part. What do you mean by dry density? the mass of soil divided by the volume of the container. So this is an important part. Now, this is a typical compaction curve, which is called as a dry density versus water content. So you can see that for this is an important part because I'll be coming back to this type of picture again. I can say that for any density, I can have two water contents. I can achieve the same density. This we call it as optimum water content. Something which is less than that, we call it as dry of optimum. Here we call this as wet of optimum. And this is also a way in which we can increase the effort to compaction. As I told you, you can put different mechanisms to compact. You can have different compaction curves, but the trend will remain the same. Now comes the important part as far as the embankment is concerned, compaction control. How do you ensure that the density of the mix is so much? How do you ensure that the water content is so much? Yes, we should have some mechanisms to do that. Generally, we use something called as core cutter method. So core cutter method is a method. So this is even transportable to the field. What you do is like you have this being placed on the field on a level place, and you use this rammer which is of 9 kg mass, push it to the ground, collect the mass of soil inside the core, and you know the dimensions of the core and you know what is the mass of the soil, you get density. You can determine the water content. So the conventional method of determining the water content is you take a known mass of soil, you put it in oven for 24 hours, you find out the decrease in mass, find out the mass of water, express it in terms of the dry mass of soil. So this is the way in which you try to determine the water content. I repeat, water content, what you have to do is like take a predetermined mass of soil, put it in oven. So whenever I put it in oven, I have to put it in a container. So accordingly, I have to reduce the weight and things like that. So take a predetermined mass, say suppose I've taken 100 grams of soil, put it in the oven for 24 hours. After the keeping it in oven for 24 hours, suppose my mass has become 95 grams. So the amount of water there is 5 grams. So 5 divided by 95, 5 divided, not 100, 5 divided by 95 is your water content. So this is how you determine. We also have another method called a sand replacement method, but generally sand replacement method is used only for cohesionless fills, because cohesive fills we can take it here, because cohesionless fill we cannot take it here because it will not retain within the core. So such cases we may use a sand replacement method. I'm not going to the experimental part of that. Now, as I told you, so this is a method wherein it requires 24 hours. You have to put it in oven, right, for determining the water content. This is difficult in the sense you should be able to know the water. For example, when you are in the field, you cannot find out a oven, because weighing balance, you get portable balances, you can take it, but you will not be able to find out what is the water content. You cannot go to a lab, immediately and things like that. So that is the reason why we have so many other equipments also. So proctor needle is one method, but proctor needle, the problem with proctor needle is like it has to be calibrated. So though I told you we cannot go to the field, for example, if I know the soil, so I have taken a soil X, the same X soil I have used it in the field. For that water content, I can use it because I know the compaction characteristics. How here what we will have is we will have a needle with a needle point, and the resistance offered by the soil to this needle point we measure. So first it should be calibrated. That is a part. Then we have another method called calcium carbide method. This is a very simple method. What we do is like we take a small, this is also requires a calibration part, but generally the calibration chart will be provided by the supplier itself. What they do is like they take some amount of soil, whatever the soil it is, and we put that into it, and we add some calcium carbide lumps also. And then what happens is like we will be getting the calcium. So what happens is like because of the reaction between the soil as well as this calcium carbide, there will be acetylene produced. And this acetylene will exert a pressure, and that pressure is measured by means of this method and calibrated to the water content. And infrared moisture meter also, what we do is like, we will keep the soil, and so this is also based upon the top measurement, wherein it is like a balanced part. You keep the soil, and as and when it is able to balance uh, whatever the balance that is kept inside, what happens is like we'll be able to know that. And here also we'll be using infrared for drying the sample. So our institution, they do have both these methods. I mean, I can say calcium carbide as well as infrared moisture meter, our institution do have. And now this is the most important part, because especially for people who are into this bund restoration and things. So whenever, how do we say that my bund is, good, my bund is a proper, whatever it is. So whenever my bund is extending up to a 3-meter height, okay, the laboratory dry density should be 15.2 kilonewton per meter cube. Please note, this is a dry density. As I told you, how do you get dry density? I know what is the mass of the soil that has gone inside. Because how do I know that? Because there is we can derive those expression by using the simple principles, okay, like we call something called phase diagram. I'm not going to those parts. So dry density, once you are able to compute, so if you are having embankment up to 3-meter height, okay, the density should not be less than 15.2 kilonewton per meter cube or 1.5 gram per cc. And embankments exceeding 3-meter height, the density should not be less than 16 kilonewton per meter cube or 1.6 gram per cc. And earthen shoulders, because especially if you are using this part, the bund, for any type of traffic part, then the density should not, dry density should not be less than 17.5 meter cube. Now, please note, so these are all, because we know that most of the bunds, they are being used by the public for some means or the other, either for movement and things. So that is why whenever we have such type of movements, and we always use one more parameter called as a strength of the soil, we also express in terms of something called as CBR. So we call it as a California Bearing Ratio Test. I repeat, we call it as California Bearing Ratio Test. And this is also being used in order to determine the suitability of our soil for the construction. And now coming to the compaction control, we have something called as a relative compaction also. Now, what do you mean by relative compaction? This is also very, very important. Because, for example, in the lab, when I showed you, I didn't tell you about the elaborate procedure over there. I had only shown you the slide. So, for example, in the lab, I deal with a compaction of 3 kg, 6 kg, 5 kg, 6 kg soil. I don't deal with more quantity of soil. But in the field, as many of you are experts itself, you deal with tons of soil, right? You don't deal with kilos, you deal with tons. And your the magnitude of the soil that you deal with is very huge. And whatever the quality control that I can get from the lab is very high, because I deal with 6 kg. I cannot get the same quality with respect to the field. So always the code specifies some amount of relaxation in the densification in the field with respect to lab. Okay, so I repeat, the code always provides some guidelines wherein we can have some relaxation in having the field density with respect to the lab. So we call that as relative compaction. Relative compaction is given by, I can say that it is rho d in the field, okay, divided by rho d in the lab. This is called as relative compaction. So in the field, I can get only 97% of the density I have achieved in the lab, or I can achieve 95%. Generally, 95 to 97% is the reasonable part. So you can see here, these are the code specifications for earthen shoulders and all. They specify that 97% of the relative compaction should be achieved. For embankment, it should be 95. Okay. Now coming to the engineering properties. So I have told you about the compaction part, which plays a very, very important role as far as the engineering properties are concerned. So the engineering properties, whatever I am dealing with, is permeability characteristics. So I can say that, so this is the compaction curve. So why I'm telling all this is because you can understand how soil classification, it is coming into picture with compaction, how it is going to link with permeability and the other parameters. So we can say that the permeability part, this is a compaction curve. So this is your compaction curve. You can see that the permeability, if you look into it, it will decrease. Okay, so permeability will be the minimum at around OMC, but generally it is to the wet of OMC, the permeability will be on a lesser end, and then it will again keep on increasing, but always onto the compaction curve. So please remember the compaction curve. So this is called as a dry side, this is a wet side. So always in the wet side, the permeability will be less. Why we should know this? You remember in the first figure I told you, we have core of a dam, we have a shell of a dam. Core of a dam, the requirement is permeability should be less. What is the purpose? The core should be able to retain its structure even in the presence of water, because it should have a very less permeability. It should not allow water to pass through it. If it allows water, then what happens? Your dam will crumble or your bund will crumble. So that is why your core, we should have a lesser permeability, whereas your shell should have a higher permeability. So clay, that is cohesive clay, will have a lower permeability. Silt will have a higher permeability than clay. Now strength. Strength always in the dry side will always have a higher strength when compared to the wet side. That is very much understood by anyone, because as I told you, if you walk on a marshy area or a soil which is containing a higher water, your feet will go down, whereas it will not happen in the other way. Now coming to swell shrinkage characteristics. So this is a compaction curve. A soil, so this is your compaction curve. A soil which is onto the wet side, you can see that it is already containing more water. So what happens? They have a tendency to shrink more. And similarly, a soil which is to the dry side, they are already having less amount of water. So they always have a susceptibility to absorb water and swell more. So I'm telling you, compaction and permeability is very, very important part. And they also, the shear strength is a very, very important part as far as the selection of material for a dam. Now coming to the, sorry, it is not deterioration, it's a, these are the steps, okay? Yeah. So coming to the construction operations, the first operation is setting out. You should be able to set out the foundation of a embankment. You should be able to dewater it, in the sense, generally we always prefer the area where you are constructing a bund should be devoid of water. So if you are having water over there, it is always advisable to remove the water. The reason is because if you have the water over there, it will be finding it difficult to place a soil and things. Otherwise, if you, it is still it is unavoidable, I think I'll be telling it later also. If it is still unavoidable, you can have to do, you have some amount of water over there and you have to construct a bund. You can use a coarser material at the base so that it will not retain water and it will always serve as a seal over there. And you should be able to strip, for example, once you are able to make the alignment, you should be able to strip the soil and store it so that we can, even if you want, we can use it later. Now, whenever we do compaction, so first and foremost thing, we have done the stripping, and also please keep in mind that time we can do the core trenching also, because as I told you, if you remember in the first slide when I showed you the embankment, I have told like wherein we can have the core, below the core, right? We have the cut-off trench. So cut-off trench is the one wherein it contains the soil which is having a very low permeability, and generally that is being constructed. So just I will go I will just go back to that slide to show you here. Yeah, this one. Yeah, basically this part, this red part. So generally they use clay of very low permeability, like for example, bentonite slurry we can use, or otherwise sometimes they even use cement grouting. So this is the part. And now let me come to my. Yeah, as I told you, this is cut off. This is okay. Now setting out, dewatering, stripping and storing of topsoil. Now compaction generally, so whenever we do this compaction, people have a tendency like, what should be the lift thickness? What should be the thickness, because, whatever the mechanism by which you do the, for example, if you are using a static roller for compaction, in that case and all, what happens is you should be able to arrive at a reasonable lift size, because any compactor that you do, it will not be able to transmit the energy to the full depth. So what happens is you should be able to identify what is a suitable lift height. Lift height means the thickness, which can be used for compacting. It should be in the lift thickness should be 200 to 250 mm generally. Now, what happens is generally whenever you make this compaction, suppose generally you know that all of us know that it is going to be embankments. Generally, they will have a trapezoidal cross section. Then how do you do this cross section as such? So what happens is either you can have, suppose you are going to have, you can even fix your boundaries. That is one way. Okay, you can have your boundaries. So generally our embankment, yeah. So this will be your cross section. So what happens is we can either have our boundaries being fixed, okay, and then knowing the width, okay, what happens is like, suppose I already know what is the slope in which I'm going to make it. Generally, what happens is it is advisable that we should not construct in full stretch. For example, if my base is going to be 10 meters, I should not make a rectangular part of 10 meter, because it is going to be so much of wastage of our time as well as human resources and things. So whatever the width that will be required, we can have it in a size such as slightly more than that. The reason why we go with slightly more width, like for example, if 10 meters of width, and suppose the width over here, yeah, suppose the width over here is a say 5 meter. Suppose the width over there is 5 meter, means it's always advisable to go for a width of around 7 to 8 meters or so. We should not go for again a width of 10 meter. The reason is because we are unnecessarily wasting our resources, and at the same time, the reason why we advise to have a slightly an outer margin is because it is very difficult to compact the edges. So the reason is, if you try to have an exact width over there and try to do the compaction, it becomes very difficult. So it will be very difficult to maintain the density. So you can compact it and later we can trim it. So generally whenever we do the trimming, it is like we have to, so we have already done, and knowing the boundaries being fixed, we can always measure it and we can always have a step cutting being made so that it will get the desired slope. Now, when suppose, as this I have already told you, if you want to construct an embankment of a water, if it is unavoidable, try to use a granular material in the base, and also you should be non-plastic. What is non-plastic? If you remember, this is something wherein the plasticity index, that is difference of liquid limit minus plastic limit, it should be 0. And uniformity coefficient, this is also a parameter which is from the like a grain size curve. So it should be less than 10. And the maximum particle size is less than 75 mm. So we can understand that the soil classification and the soil characterization plays a very, very important role in the selection of material for a bund. Now, just these are a small snapshots on how exactly you want to construct. So suppose I want to widen my embankment. So suppose this is my older embankment. So this is my, so you can see here, this is my older embankment. And now I want to widen my embankment. So this is going to be my new embankment. So now what happens is, so this is the existing and this is my new one. So what happens is, in such cases, you just don't put the new material on the edges. You just don't put the new material on the edges. It will never reach a proper bonding. What you have to do is, right, we have to have some benches. We should have some bench construction wherein we will be having some benches being constructed into the existing bund, so that there will be normally this bench construction itself will be 0.3 to 0.6 meters, and we should be able to have a proper bonding between the new one as well as the old one. And similarly, suppose we want to have a continuously a part of the bund to be constructed. You want to increase it only by one part, the downstream part or so. So this is one way. You can have a light fill being constructed, but please note, we should be able to have the the step cutting part over there, or otherwise you can have a geosynthetic reinforcement. The reason for the geosynthetic reinforcement is like it can serve as an anchor, and at the same time it provides a tensile strength for the embankment also. And suppose here I want to widen, provide a sheet pile wall or a cutoff wall. So whenever I'm telling a cutoff wall is something wherein it will prevent the water from seeping. So what happens if water seep from the base itself, your entire dam will collapse, right? So we should be able to provide a sheet pile, and thereby you should be able to provide the bund over here, and by providing a proper strengthening of the foundation. You can even provide something called as a sand drains or a columns over here to provide the stability for this part and construct a bund. And here we also have something called as a fill being constructed, because here this is the case wherein you are having one embankment is there and there is a smaller embankment, you can provide a fill. Here there is a term called as preloading being used over here. I will just tell a few words in this line, because preloading means, say for example, whenever you have a bund or anything that is being constructed, what happens is you are applying a load onto a surface, right? So what happens if you are applying a load onto a surface? Generally, the surface will respond, right? It will be trying to, it will tie. What happens is like, I have not told about those things in detail in the previous slide because I didn't want to make it more complicated or so. So what happens is, generally in any soil, as I told you, it will be containing soil grains, water, as well as air. Now, suppose it is a saturated soil. So when I'm telling a saturated soil, especially below lake soil in the lake side, means it will be generally a saturated soil because it's full of, all voids are filled with water. So what happens is you apply a pressure on top of it. So what happens is like this water, it will always try to take this entire load being applied to it. So when you are, I repeat, I have a saturated soil. A saturated soil is the one which contains all the voids are filled with water, and I'm applying a load onto it. What happens? The water will take the entire load coming on it. Because the water is a material that is more of a fluid kind, it will take the entire load. So what happens? The pressure so developed in water, we call it as pore water pressure. If the pore water pressure, because of this pore water pressure, what happens is like once you apply the load, the pore water pressure starts seeping outside because of this excess pressure to dissipate. So because of that only, there will be lots of settlements that will be coming into picture. So in order to avoid such things, what we do is like first itself we apply a load and ensure that that much of pressure is applied to it. The settlement, everything happens in prior, so that when you construct the embankment, there will be no such settlement happening. So that is called as preloading. So this will be coming into a separate topic itself, which is called as consolidation. It is like something similar to compaction. So compaction deals with expulsion of air. Consolidation deals with expulsion of water. Now, how do you treat embankment slopes? So whenever I want to treat my slope, okay, so always you would have seen a riprap, right? That is the most commonly seen material. So the reason why we use the riprap itself is because these ripraps, okay, they can withstand the waves energy, and at the same time, being like larger in size, it will be able to stay there as well. And in suppose you don't have that material, what are the alternative materials you can go ahead with that? You can have a simple vegetative turfing. You can have a simple vegetative turfing because, as you all know, the roots of the plants will be helpful in holding the soil together and retaining its place. Or we can even have a ready-made turf or a grass also being placed. Then a straw with a cow dung or a wood shavings or sawdust mulch. So mulch is nothing but something that will isolate the material. Okay, so that is what exactly it is. So that also we can use it for protecting. And you can even use asphalt mulch technique as an aid to vegetative turfing. What does it mean is, first we can use your, you can level your slopes, everything. Once you level the slopes, you can put the seeds to it. I mean the plant seeds or whatever you want, you can grow to, you can put it. You can level the surface, whatever it is, and you can provide the once it starts sprouting up, you can even provide the asphalt surfacing over there, so that what happens, the plants will retain there, and this will be able to isolate the vegetative part from that of the the remaining part, and it will be giving an overall protection to the side slope. Now, with all this geonet and those materials are also coming up. We have jute netting, coir netting, and things like that. And in fact, if you look into it in our the Mysore to Gundur road itself, no, Gundalpet road itself, we can see that there you can see lots of water bodies over there, and there all these. So our highway runs in between those two water bodies itself, and they have tried to use this type of geonets for stabilizing the slopes over there. In fact, during the highway construction expansion part itself, we could have seen where how they unroll it, how they spread it, and how do I do that anchoring part, and then now we cannot make out because it's full of vegetative part. The advantage if you use with the coir netting or jute netting is like they will get they're being biodegradable. They will go away after some time. So that is also a challenge. Your slope should be equally stable over there. Geonet kind of thing, which is a polymeric material, those materials will stay over there. So that's the difference. And you can have different. So generally, whenever you look into it, the embankment slopes, as I told you, we generally, I have shown the first picture wherein there is only a one uniform slope, wherein it is either 1:2, I mean 2 horizontal to 1 vertical, or 1.5 horizontal to 1 vertical. But in fact, the code, in fact, if you look into it, by keeping in mind the erodibility part, they even highlight on the differences in the grade that should be maintained in the slope. Okay, so because if you provide a uniform slope, the chances for erosion is more. And if you really feel like, no, because that slope, steepness of the slope can be reduced, if you want to have a proper gradation part, we can even have different slopes. So as I told you, the acknowledgements to code books. So wherein these are all materials that are being taken for code books, wherein we have to take into account how exactly the BUND should be placed. Now, even these are the general types of embankments based upon the types of infills. So this is a homogeneous earth fill, and so this is wherein we are having a zone part, so rock fill part in the downstream end, and this is a core part, and this is again a puddle core, so center part, and narrow part itself in the core. So you can see here majority of the part they highlight in the presence of either a core part or a rock rock fill part in the downstream end and things like that. And nowadays, the most of the constructions that we do will be either in zoned earth fill and zoned earth and rock fill, or central earth and rock fill type, and things like that. Now, coming to embankment failures. So, what are the reasons for which we have this embankment failures? So you can see here This is nothing but the high flood level. So from, if you don't have, if you are providing a homogeneous cross section, what happens is the water from the upstream end will try to find the way to get dispersed into the lower, I mean the downstream end, by finding a shortest path like this. So what happens is, if we are able to provide a core, suppose suppose I am able to provide a core over here. So what happens is, from the upstream side, what happens is this water cannot come down like this, because it will be coming in this way, and then it will come here, wherein I may even have my drainage part, and this pressure will get dispatched. Okay, so this line, this is nothing but this line, we call it as a phreatic line. Phreatic line is nothing but indicating the pressure of the water, hydrostatic pressure that is existent within the soil. And what happens is, if you provide a core, what happens is like it cannot pass through this because core is impervious. So the advantage is that this core part will get retained. So this is an advantage that we get, especially if you are able to have it. So our objective finally is that any of this hydrostatic pressure that is there, it should get dispatched into the lower end without causing any damage. Yeah. So this is also a typical case. So I am having a core here, but the problem with this is my core has got a crack. It has got a crack. My water is moving from the upstream to the downstream end, and this can cause a failure. What over here? See, my foundation itself is gone. Water seeping, and water seeping, and my stability of the dam itself is over. So these are some of the important parts that we have to take care, and especially these things we have to take care, especially since we are dealing with the lakes, that localized area itself, those people can take care of that. Now you can see here, this is a pipeline that is there, okay, for some reason or the other. Now this is a water conveying conduit. So this part, from here, water is seeping to the base. Definitely the dam will fail. The reason is because the dam is subjected to, the foundation itself is subjected to danger. Now coming to the distresses in dams. So what are the reasons for the failure in dams? So what we have seen, what are the chances for failure in the dams, or I can say the earth embankments. So these reasons can be categorized into deterioration in the foundation or deterioration in the dam body. Now, deterioration in the foundation, it can be because of percolation and internal erosion, or it can be due to the loss of shear strength, or it can be due to deformation and subsidence. Please note, I have told here about deformation and subsidence, that is in terms of consolidation. Okay, so that is the one that is associated over here. Now coming to deterioration in dam body, it is again percolation and internal erosion. Then it can be because of the default in the slope protection, differential movements, interface between embankments, concrete or steel or structure or adjoining embankments, as I told in the last picture, wherein the pipe, right, how exactly it can happen, or upstream slip or a downstream slip. So slip that is happening on the upstream or downstream end. I think I repeated it, yeah. Now coming to percolation and internal erosion, this is because of the inadequacy in existing seepage control system. So I have shown you how exactly the phreatic line is coming. So if the phreatic line is not is going to interfere with the stability, definitely your dam is, embankment is going to fail. Excessive pore pressure. So what happens is, like, if you have not whenever I've told you, like, what exactly is pore pressure is nothing but the moment you apply construct an embankment or so, the water will take in the pressure and it will be having a very high amount of pore pressure. So what happens if you are having some mechanisms to relieve this pore pressure, like how exactly I've shown you in the phreatic line, in the toe end we can provide a grain filter. So that and all, if it is there, the moment it reaches the downstream base, the pressure gets dissipated, because the why the pressure is getting developed, because the water is retaining over there. That's the reason. So sandy soils or gravelly soils and all will not retain the pressure. They will get relieved of it because they have a very high permeability. So those materials, the use of such type of filter medium, that is the meaning. Then loss of shear strength. So decrease in shear strength, because the moment you have a higher pore pressure, the strength of the soil will decrease, because always the water will try to take in the more pressure, and the soil will not be able to take it. So this is what exactly happens during earthquake and all, right, wherein the pore pressure increases drastically, and we have like something called as liquefaction that happens. And we have deformation and subsidence, that is an excessive differential settlement. Now coming to the dam body, what are the reasons for the same? Then, as I told you, percolation and internal erosion, I told you deficiency in construction or inferior construction, choice of improper materials, inadequacy of drainage filters, use of undesirable construction materials. What does it mean? Internal choice of undesirable construction materials means the core should be of a very high very low permeability, and the shell should be of very high permeability. Then we should have some slope protection mechanisms, like which will not be decomposing under weathering, and unforeseen precipitation or waves, differential movements, inadequate protective drainage filter layers, splashing due to wave action, presence of small size stones, because these stones will easily get worn out, and accordingly the stability will also be in a stake. Then differential movements, it can be like again interface between the embankments of concrete or steel. Differential movements I've already told, that consolidation settlement, or because of improper compaction. And then interface between the embankments, like as I told you, like I have shown the picture, right, wherein the from the pipe top itself you can have some seepage and the stability of the embankment going. And differential movement, again, I think I made a wrong choice in animation. So downstream as well as upstream slips. So it is because of excess poor water pressure, inadequate shear strength, poor construction, liquefaction, and saturation due to sustained rainfall. So these things and all are very easy, right? We can all tell what are the mechanisms and things, but the major choice lies in how can you detect it, right? How can we have a how can we know whether our slope, our bund is going to fail or not? Direct observation and monitoring. So this comes with the responsibility of the localites as well as the community itself, wherein it is their responsibility to ensure that the lake is well protected by means of these bunds. Observation of piping, erosion of the bunds, because people have a tendency to ignore, but at the same time identify the piping. So when I'm telling piping means you can able to identify wherein the water will be seeping in, and excessive growth of vegetation because of the excess amount of water, bulging or depression of slopes and berms. Animal burrows, we know this rats, right? They will make a huge burrows inside, and that can even lead to a failure. And deterioration of riprap. Okay, so cracks in the riprap material and things. And it is also good that you also, because we know that the chances for this failure is not only restricted to the surface, it can even happen from below. So it is always good that we have some observations where, there is some underwater observations, especially the heel as well as the heel end as well as the toe end, can we have a observation on the same. Now, we should also do some sort of measurements, periodic and systematic measurements, in the sense either in terms of water, density, or in terms of the water content that is there. And even we can have even a compaction control, especially with respect to any of the field observations that is there. And we should also be able to take some samples from the field and also get it checked. And it's always important that it should be there. And because as I told you, people always have a tendency wherein, the sludge that is being collected. For example, if I'm doing a lake restoration project, what happens is like they have the sludge that is being developed, and this sludge, I can use it as a fill material, but I have to ensure that that material is having a properly stabilized, because those type of sludges will have high compressibility, and they will be always subjected to decay. And because of that, what happens is like over a period, the compression that it will undergo, I mean the compressibility will be very high. So those things and all also should be considered when you deal with it. Now, how do you do a remedy for the same? Now, whenever you do a remedial measure, see, it's always good to have a close monitoring of all the things, but it is very difficult to do that, because you should know, because everyone is having their own work and all those things. But at the same time, definitely there are some people who they take voluntarily all these actions. So we should be able to know what is the risk element that is there, because how many people are going to get affected, and what is the storage capacity, what is the foundation, okay? And similarly, what are the materials and methods? So what, because suppose we have used some material, inferior material in the construction, it is our duty to ensure that it is dam is being properly monitored, the bund is properly monitored. So we cannot, because we ourselves have made a new choice of a material. Now, how do we do a treatment for seepage? Generally, for seepage, we treat by means of grouting. So grouting, as I told you, is a case wherein we have a concrete, or a cement mortar being poured into it so that it will remain as a water sealant. Or we can even have a positive cutoff or a partial cutoff. So what is a cutoff? As I told you, cutoff is a case wherein it prevents the water from upstream to going to the downstream end. Use of a geomembrane in the upstream end. So geomembrane is something wherein geosynthetic material which is having a very low permeability. So that can also protect your sites. And removing and rebuilding of damaged parts. And so this is some of the typical cases. So you can see here a cutoff wall. So that is there. This already is shown. And especially, so this is very important, especially when here also you can see it's a waste dump site. Also, you can have a bunt over here, which need not be necessary. Here also you can see the water level is too high or whatever things it is. Now this is a case of a dump. So a dam, wherein here you can have a. Now these are also a typical figure. So wherein you can have a so this is nothing but the first, this is one is nothing but the geomembrane being anchored, and this is your geomembrane part, this dotted part, and you are having your riprap kind of material also being provided over there. And so this is how we can use it for protecting the upstream end. Now, as I told you, when we are having a higher phreatic line, so the phreatic line, it should be ensured that it should not interfere with the core of the dam. You should be having a vertical drain. So what is a vertical drain? Vertical drain is a drain which is constructed made up of sand or any coarser material, generally sand, so that it will be able to dissipate the excess pore water pressure. Provision of a new filter section with berm. Providing an inclined chimney, I have a sketch for it. I will show you that. And providing a filter and rock toe at the downstream, and strengthening by grouting, filling in fractures. So this is also a case wherein I can have a vertical drain being provided over here. So this is my drain. So here itself, I can ensure that my phreatic line will intersect up to here. So from here, I can have a vertical drain through which the water will get permeated. So so this is a way you can ensure that, your phreatic line is getting intercepted by the drain. And you can even see that the filter material is being provided in the toe also, so that, you will be having the toe end also being protected, and also berm kind of construction. So this is nothing but the inclined, like a filter that they were telling. We can have a filter medium that will be moving on the sides itself, so that, so this is your embankment. So one is your existing profile, and two is going to be your new profile. So you're going to expand your embankment by a part, and by providing a, the sliding type of filter, so that, so now here our objective will be like it need to reach only till here, so that it will again get dispersed off. So what are the different methods? I have already told you these things earlier, but just as a codal. So these are the codes as such given by the code itself. So that's why I've taken it as such. So partial repair with the same material, or enlarging the upstream protection, enlarging the upstream protection zone by dumping. So this also we have seen, I've already shown the sketches and all, wherein we can protect the upstream and replacement of slope protection and partially replacing the upstream protection. So these are all the gullies that are there. So we can get a renovation of that. And similarly, this was nothing but the expansion part. And so this is also a case wherein I'm dividing my embankment, and I'm providing expanding this, providing a protection to the upstream end, and even the heel end also I'm providing some drains. And so these are the different things. Now slope stabilization and raising the bund height. So this is also very, very important. So upstream stabilization, it can be in terms of flattening of slopes or by means of grouting or cement grout, restoration of failed slopes using geosynthetic materials, and providing additional earth fill with horizontal filters. And downstream, we can even install a drainage system. We can flatten, reinforce the earth. Reinforcing of the earth means is basically use of geosynthetics. Stone pitching again can be provided. Providing an effective rainwater drainage system, and providing good and effective turfing, and employment of any other treatment mechanism. So with these things, I would just like to conclude my session by saying that the importance of bund or earthen embankment in lake restoration is very important. And selection of earth for the bund is also an important parameter. Construction steps, how should we construct? What are the distresses and how should we measure it? And what are the remedial measures? We do have a Hulimavu Lake itself, wherein the bund has breached and several houses have been flooded in the year of 2019 itself. So this shows the importance of this, protection of the bund as a part of lake restoration. So thank you everyone.